The second substitution mechanism is called an SN1, which stands for S for substitution and for nucleophilic, and 1 is unimolecular, meaning the reaction rate depends only on the concentration of one molecule. And of course, in this case, you will find out that it's the halide, the alkyl halide. So here's an example. This one could not be an SN2 mechanism for a few reasons. Number one is that this is, so again, we're going to say not an SN2 reaction. Number one is that you have a tertiary alkyl halide. And SN2 reactions do not take place with tertiary. This is tertiary. Three carbons. Number two is that your nucleophile is a bad nucleophile. So this is a bad nucleophile. It's uncharged. It's an alcohol similar to water. So it's a bad nucleophile. So this reaction, as what we call SN1, is generally referred to as solvolysis, meaning the solvent is used to make a new compound. The solvent in this case is your nucleophile. So upon measurement, experimental measurement, we find that the rate only depends on the alkyl halide. In this case, it's the tert-butyl, this right here. This is tert-butyl bromide, because that's a butyl group. So we conclude that the reaction is first order. Any involvement of the solvent in the reaction cannot be detected in the rate law because the concentration of the solvent is essentially constant. However, the nature of the solvent does play a critical role in this reaction. We will find out, especially when we talk about polar aprotic and polar protic. So again, the reaction is SN1, substitution, nucleophilic, and unimolecular. So if the concentration of the alkyl halide doubles, the reaction rate doubles. If the concentration of the solvent doubles, the rate is unaffected because, again, it's constant, doesn't play a role. So let's look at the mechanism. How does the mechanism look like? So we will just use a generic reaction here. The first step is the rate limiting step. This is the slowest step, and it is the dissociation or the bond breakage between carbon and the leaving group or the halogen. So the leaving group departs the alkyl halide. So you would get this. You should be able to tell what charges are now on each. This would be a positive, and this would be a negative. So that's your first step in the mechanism. It's no longer a one-step mechanism. And then the second step, which is very fast, is your nucleophile, which is the solvent. But we're going to use nucleophile. Attacks the electrophilic carbon. right there. Let's just put it in blue to keep it consistent here. So before we move on, again, this is our rate limiting step. So this is the slowest. And this would be the fastest step. Let's look at the energy diagram of this reaction right here, because it's a more exact energy diagram. So you'd find that the first step, the breaking of the halogen carbon bond, it would be the slowest step. So if we were to draw this, this would be EA1, and look how slow it is. How slow it is. So here's your slowest step, or the rate limiting. Of course, the difference here is delta H, so it's still an exothermic reaction. Now, I'm not going to be too overly concerned with the transition states. I'm going to just draw the first one. I'm not going to ask you to draw all of them. Just be able to draw at least the first one. The mechanism you have to be able to draw, but for the first one, it's simply, again, the breaking of Br CH3 bond, the C bond. Here's your intermediate, the carbocation. Of course, you have another transition state, and on and on and on. So of course, each one would have, its own EA. So that would be EA2, and that would be EA3. Notice how we're applying what we learned to here. So be able to draw the transition state for the slowest step.